Welcome to this video on Z-scores. After watching this video, you will be able to answer the following questions. What is a Z-score? How do you calculate a Z-score? What does a negative Z-score tell you? What does a positive Z-score tell you? What Z-scores are considered usual? What Z-scores are considered unusual? And why do we use Z-scores? Let's get started. A Z-score is a measure of the number of standard deviations a specific data point is away from the mean. Here's the general formula for a Z-score. If we're working with population data, in other words, the population mean and the population standard deviation, these are the symbols we will use. If we're working with sample mean and the sample standard deviation, then these are the symbols that we will use. These equations are actually identical. The only difference is that the symbols we're using to represent the mean and the standard deviation are different. So let's review the symbols and what they mean. Z in both cases is a unitless quantity that measures the number of standard deviations a data point is away from the mean. Both equations, as you can see, have this variable x in them. In both cases, x is representing a specific data value. In the first equation, you can see that we have the symbol. It somewhat resembles the regular letter U. It's actually the Greek letter mu, and it's the Greek letter for their lowercase m. It's pronounced with the M sound, so it makes sense that the M would represent the population mean. Also under the population mean and standard deviation, we have this symbol down here. It is actually the lowercase Greek letter for S, and it's called sigma. So it makes sense that the S letter would stand for standard deviation. So sigma is the population standard deviation. If you come over here on the right-hand side, you can see that instead of using a Greek letter mu to represent the population standard deviation, we are now using the symbol x bar, and that represents our sample mean. And then on the bottom, S represents sample standard deviation. Now, at this time, your instructor may or may not be differentiating between a population and a sample. However, as you progress in your study of statistics, it's really a great idea to become aware of these and to be familiar with different symbols, because at some point, if you actually take a statistics course, you will be asked to differentiate between a population and a sample, and you will be using all of these symbols. So let's keep going. If we look at the pattern here and what the Z-score is really telling us, we can see that the Z-score takes a specific data value and it asks a question. It says, how far is this specific data value from the mean? And then it compares that distance to the standard deviation. Another way to think about this is to say that we are finding how far a single data point is from the mean, and then we're comparing that to the average distance from the mean. And that's what a Z-score does. So suppose you scored a 95% on a test. The class average was 80%, and the class standard deviation was 10%. Did you score above average or below average? If you want, as we go through these examples, you can pause the video and write down or say your answer out loud, and then unpause the video and find out if you were correct. Then we also want to know how far from average did you score relative to the rest of the class. So once again, we're going to use our Z-score equation to answer these questions. So remember, X represents our specific data value. In this example, our 95, the individual score that you scored, is the data point that we're curious about. So in this example, X is going to be 95. The population mean will treat the rest of the class as a population, and the population mean was 80%. So our mu, or population mean, is going to be 80%. Then we have our population standard deviation, and again, that would be 10%. When we put that all together into an equation, we find that 95 minus 80 is 15. 15% over 10% is 1.5. So, did you score above or below average? Well, clearly 95 is above 80. Also, you have a positive z-score, so we know that you scored above average. And how far above average did you score? Well, the z-score tells you that you scored 1.5 standard deviations above average. Let's do a second example. So this time, suppose you scored a 75% on the test. And again, the class average was 80% and the standard deviation was 10. So again, we ask, did you score above or below average? And how far from average did you score relative to the rest of the class? So in this case, our specific data value that we're curious about is this 75%. We are comparing this to the population mean of 80% and a standard deviation of 10%. When we plug those values in, we can see that 75 is less than 80. So that gives us a negative 5% difference between your score and the rest of the class. And then we divide that by the average distance from the mean, and we end up with a z-score of negative 0.5. That means that you scored 1/2 of a standard deviation or 0.5 standard deviations below average. So again, a z-score measures the number of standard deviations a specific data point is from the mean. A positive z-score means that the data point in question is above average or greater than the mean. A negative z-score means that the data point in question is below average or less than the mean. A z-score of 0 means the data point is equal to the mean. So let's look at the z-scores in the normal curve. So if you watch some of these previous videos where we're discussing the empirical rule and the normal curve, you should be familiar with this image right here. Notice when we labeled this, we started with the mean. We put the mean in the middle, and then we added standard deviations for each tick mark to the right, and we subtracted standard deviations for each tick mark to the left. So what if we normalize or standardize this information, and instead of down here writing our mean and standard deviations, we put z-scores along this horizontal axis? What would that look like? So that's what we've done here. Again, we've taken a graph where we have values specific to the problem, and we've changed that to have normalized unitless z-scores. So let's look at this for a minute and make sure we understand what's happening here. So as you can see, a z-score of 0 is right in the middle. So instead of putting the mean of our population in the middle, we have a z-score of 0. That means we are 0 units to the left or right of the mean. We are exactly at the mean. As we move to the right, a z-score of 1 indicates that we are 1 standard deviation above the mean. And then we keep going, we have a standard deviation, a z-score of 2, which is 2 standard deviations above the mean, and then a z-score of 3 would be 3 standard deviations above the mean. Likewise, if we start at the mean and go left, we would have a z-score of -1. That means that we are 1 standard deviation below the mean, and so on. Let's look at how z-scores can tell us about whether we have a usual or unusual value. So again, this is really meaningless unless you are working with data that is normally distributed. You can't really use z-scores if you don't have populations that are normally distributed, or of course, if you're using the central limit theorem, which is covered in a different video. So realize that 95% of your data is between positive and -2 standard deviations. In other words, 95% of the data lies within 2 standard deviations of the mean. So what we do is we say that anything in this middle 95% of our data is considered usual or not surprising. However, if anything lies beyond or more than 2 standard deviations to the right of our mean, we are surprised. And if we find any z-score that is smaller than -2, meaning that it is more than 2 standard deviations to the left of our mean, then that is surprising or unusual. And that is the metric we use to determine if a measurement is usual or unusual. So let's do a few specific examples. Is a z-score of 1.5 surprising? Well, let's look at it. As you can see from the yellow arrow here, a z-score of 1.5 lies within that middle 95%, so it is not surprising. What about a z-score of 2.5? Hopefully you can see that 2.5 is outside that 95% of data, so it is surprising that that is not a z-score between negative and positive 2. It is outside that window. How about a z-score of negative 1/2? Again, as you can see here, the little yellow arrow shows us that it's inside that middle 95% of data, so it is not surprising. Lastly, what if we had a z-score of negative 3? Again, you can see that this is outside of that negative 2 to positive 2 window, so this would be a surprising or unusually large z-score. So the last thing we want to talk about before we end this video is why z-scores are so useful and helpful. And the answer is that they allow us to compare completely different things. They give us a unitless measure of how far from average a measurement is. So let's use this last example to compare the Orioles and the Ravens, two completely different sports teams. So as you probably know, the Orioles are a baseball team and the Ravens are a football team. So we have some data here. If you'd like, you can pause the video and read through this on your own. But basically, we're given a batting average for the Baltimore Orioles, and we're given the average number of points per game for the Baltimore Ravens. So if you think about the data that we're given, they're completely different values. And if we were to graph them on a normal curve, the batting average normal curve would look like this, with a mean in the middle and then the standard deviations to the left and right. And the Ravens normal curve would look, again, completely different, where we're graphing points per game. So the problem here is that we are graphing completely different things, and until we normalize both scores, we can't compare them. And the way to normalize both scores, as I mentioned earlier, is to use a z-score. So if you go back to the question where it explained what the batting average was for the Orioles, we can calculate the z-score of the Orioles. So their specific batting average was 0.256. We subtract off the mean and then divide by the standard deviation to get a z-score of 0.45. We can do a similar thing here where we have 25.6 minus 22.58 divided by the standard deviation of the whole NFL team, and we find that the Ravens actually have a z-score of 0.68. So now we can take these z-scores, these standardized, unitless, normalized scores, and we can actually plot them on the same standardized normal curve. Doing that, we see that the Orioles scored 0.45 standard deviations above the mean, and the Ravens scored 0.68 standard deviations above the mean. So whose z-score was slightly more extreme, slightly more extraordinary? Hopefully you can see from this picture that the Ravens' score was slightly more extraordinary, slightly more above average. So even though you can't compare the Orioles and the Ravens to each other directly, what you can do is you can compare the Orioles to the other teams in Major League Baseball. You can compare the Ravens to all the other teams in the NFL, and then we can use these z-scores, and now we can really compare them and say, relative to the other teams, who has a more extraordinary performance. And again, you can see the Ravens z-score is slightly higher, so they would be the more extraordinary team.